Danielle Woodruff, to give us the evolution of arc spark OES. Thank you very much.
Thank you. So first I'll give you a bit of an introduction to Spectro. I've been with the company about 2 years now, selling the arc spark instruments. So Spectro is one of the world leading suppliers of analytical instruments. I deal with our arc spark instruments, but we also supply ICP OES, ICP MS, and XRF. So the agenda and what I'm going to talk about. So we're going to cover the importance of elemental analysis, the actual technique, and then some of the history of the technique, the early discoveries leading up to it, and then some of the later developments, such as the different detector types. So why is elemental analysis important? It ensures precise alloy composition for mechanical properties. It guarantees compliance with customer specs or global standards. It reduces the amount of scrap and rework, which saves costs. It also improves safety and reliability of finished products. So when should we use it? We can use it as process control, so you can adjust the melt composition in real time, and then you know when your melt's finished and ready to pour. For quality assurance, as a last check before finished parts go out. For sorting and recycling, so it can be used on scrap yards when you have big piles of scrap and you're not sure what they all are. And for failure investigation, so if there's a failure, it can help you understand why and if it's anything to do with the composition of the alloy. So arc spark OES. Arc spark OES can be used for electrically conducting solid metal samples. It has fast analysis times, which makes it great for monitoring melt composition, and minimal sample prep. So it's usually grinding for harder metals like iron, or you can do some milling if you have something softer like aluminium or copper. It can analyze elements from ppm ranges up to 100%. And they come in different forms. So you can have mobile and portable analyzers. So you can take these to big parts for incoming inspection. These use analysis for either arc, which is under air. So if you're looking for a quick check or you're sorting through a big pile of metals, you might use arc analysis. Spark analysis is much more precise. So that's performed under argon. And that's all that's used in the stationary instruments. Stationary instruments are always spark. So how did it come about? Firstly, Isaac Newton in the 17th century discovered that sunlight can be dispersed by a prism. It can then be combined back into white light by the placing a second prism in the light path. This and some other features of light made Newton wonder if light is a particle, and wave theory wasn't well understood back then. After this, Huygens observed diffraction and interference and qualified it as a wave. Later, Hertz discovered that light is part of the electromagnetic spectrum. It has key properties such as frequency and wavelength. Spectroscopy always uses wavelength in nanometers. So is it a wave or is it a particle? Einstein then discovered quantum theory along with Heisenberg. So light shows properties of both waves and particles, and spectrometers take advantage of both of these. So we take advantage of the light properties by using things like diffraction gratings to direct the light to the detectors. And we also take advantage of the photoelectric effect, which is particle property, but there'll be more on that later. So the very first foundations of spectroscopy, Bunsen and Kirchhoff, so that's Bunsen as in Bunsen burner, discovered that flames can be coloured by salts. and depending on the composition of the salt, the flame would be a different colour. Fraunhofer had previously discovered that there were absorption lines in sunlight, and during the experiments performed by Bunsen and Kirchhoff, they could match these dark lines to the elements because the missing wavelengths corresponded to each element, and they absorbed or emitted the light at the same wavelength. So this was the basis for chemical analysis. So what are the principles of spark OES? In OES, we focus on elements and not molecules, so actually individual elements. As you all know, elements are comprised of atoms, which are made up of neutrons, protons, and electrons. In spark OES, we only focus on the outer shell electrons. So first, the atoms have to be excited. So this requires external energy. So in spark OES, the spark heats the atoms up into a plasma in the spark stand. As the atoms become excited, the electrons move to higher energy orbits. This makes them very unstable, so they quickly revert back to the ground state, but on doing so, they release energy as photons. And each element emits a photon at a specific wavelength. So how does a spectrometer work? A spectrometer will collect the light that's emitted from the excited atoms and direct them to detectors such as CCDs, PMTs, or CMOS sensors, but we'll speak more about them later. These detectors measure the intensity of each specific spectral line. The measured light intensity can then be compared with a calibration curve to give you a concentration result. So, in summary, the main structural groups of a spectrometer are your excitation source, which in this case would be the spark, your optical system, which separates the light into different wavelengths, so where your diffraction grating is. In spark OES, there's typically two different optical systems. So there's a UV optic, which measures down in the UV range. This has to be purged with gas or under vacuum, as oxygen and other elements in air can actually absorb some of that light. And an air optic, which measures visible light. You also need a calibration. So when you get your light intensities, it's compared to a calibration curve made up of known samples. So you know what intensity corresponds with what concentration. And a computer and software to give you the result and do all that calculation for you. So very early spectrometers, we used a photographic plate. The photographic plate would be used to collect all the spectral lines, and then it'd be taken away and developed like a photograph. This was then manually analysed. So obviously this was quite time consuming, and it took dedicated, skilled scientists. It was mainly reserved for scientists and researchers. Later though, photomultiplier tubes were developed. Soon after, these were used in spark OES spectrometers, and this was the first step into allowing real-time analysis. And they began getting popular with foundries. And this is because it allowed precise quality control, so you can control the composition of your melt in real time. You know when to pour, and it can save costs. Obviously, in turn, that increased efficiency and productivity. It reduced errors and waste, and it minimized costly mix-ups. And this, in turn, led to increased alloy production. So once foundries had confidence in their ability to precisely control material composition, they can expand their product lines, and this led to market competitiveness. So how does a photomultiplier tube work? Light enters the tube, which consists of evacuated glass housing, and strikes a photocathode. And then, as you can see in the diagram below, the photocathode ejects an electron. So this is the photoelectron effect. These electrons are then directed towards dynos, which multiply and intensify the signal, which is then converted into an electronic signal. So the advantages of PMT tubes: they're relatively robust, they've got proven reliability, they've been used in OES instruments for a long time now, good speed of measurement, and really good trace element detection. There are, however, some limitations. One PMT works for one emission line only, so that limits the total number of detectable elements. Typical PMT analyzers have a maximum of around 80 wavelengths, but this isn't equivalent to 80 elements, as a lot of elements can use 2 or 3 lines, depending what works best for the concentration range. So if you're doing multi-matrix analysis, it quickly takes up space and uses up capacity. Adding or removing elements, if you wanted to expand product lines, requires major hardware changes. So the instrument would have to be shipped back to add more PMT tubes. Wasn't always possible, and obviously it's expensive. So in short, the PMT-based systems lack flexibility, and the configuration is basically locked at the factory. So during this time, Spectro was founded. So Spectro produced a mobile instrument that you can see there, which is like 250 kilograms. And it was started as a 3-man company. This Spectro test instrument was developed with a list of expectations from steel producers. One of the early developments were developments in the UV optics. So as I mentioned before, they have to either be evacuated with vacuum or purged with gas. So initially they were all a combination of vacuum and air optics, so the UV range would be under vacuum. There were some problems with oil contamination from back diffusion of the pumps. So Spectro initially used nitrogen purged optics, and later we improved this with argon purged optics. You already had argon for the spark stand, and there was still some oxygen and things in the nitrogen, so you improved the cleanliness of the optic by using that. It also helped reduce maintenance costs because oxidation doesn't really happen in an argon atmosphere. So of the parts inside the optic, the gratings, it'll prevent oxidation. So then charge-coupled devices came along. So these were invented in 1969, and initially they were only used in cameras. A CCD is a solid-state integrated circuit, but it contains an array of thousands of pixels on a silicon substrate. Capture light and then convert it into an electrical charge. The more light and higher the intensity, the greater the charge. Each pixel measures light intensity at its location. And then the signals are all processed by readout electronics, but the signal has to be passed along the chip and then read out, so they were a bit slower. The main advantage of this was that it can detect many wavelengths simultaneously. So you can measure the whole interesting wavelength range. So you can have multi-element and multi-matrix capability. So what were the drawbacks? Pure CCD systems just couldn't match PMTs for ultra-low detection limits. So some of the bigger instruments used hybrid systems, so you used a combination of PMT tubes and CCD detectors. The advent of CCDs allowed single sample standardization. So this uses a single sample instead of multiple samples, where in the past you'd have to analyze multiple samples of each alloy type at a high and a low range. So this sped things up. So how it works, you'd analyze your iCal sample, which comes with the instrument. It's usually a tool steel, but it can be copper if you milling instead of grinding. when you've analysed this, the system then compares it to a master spectrum, and it can measure the drift and the peak intensity, and then automatically reset it back to how the instrument was on day one. So this was faster, and it improved stability and reduced downtime. Further improvements were made with iCal 2.0. So this still worked in the same way as iCal 1.0, but with the addition that it included real-time corrections. So at the start of each measurement, it'll look at the peak intensity and drift and determine if anything's happened. And if it's within a certain tolerance, it'll just automatically set it back. So this meant there's long-term stability with minimal operator intervention. The next detector, and this is one that we use in our instruments at the moment. So complementary metal oxide semiconductors or CMOS detectors. So each pixel now has its own amplifier and readout system. So this makes these detector types faster. And it converts light into electrical signals directly on the sensor. So what are the advantages over CCDs? So you have a higher data processing speed, some noise reduction, and this has enabled instruments like the Spectro Lab S, which is a high-end stationary metal analyzer. So it has the features that could only be developed with PMT tubes in the past. So now CMOS rivals and often surpasses PMT tubes. And this reverses the belief that PMT tubes are inherently superior. So you still have your maximum flexibility, so we can still measure the complete range of wavelengths. There's no compromises, so if you have closely adjacent lines, you can get interferences. But if you're measuring the whole range, you can just use a different line for that element. So you can add new elements and new matrices just with software. So this can all be done on site. There's no need to send the spectrometer anywhere. Software can be added, and you can have the calibrations for different bases. Historically, PMTs dominated trace element detection. But now with CMOS detectors and the faster speeds that they work at, we can do things that used to be reserved only for PMT detector types. The first is time-resolved spectroscopy. So in the spark, you get good and bad radiation. The good radiation is caused by excited atoms moving electrons to a higher shell and ejecting a photon. But you also get the recombination of ions. To prevent this, when the charge conduction phase is stopped, so when the spark goes off, the ions are removed, there's no free electrons, but you can still analyze the light coming from the excited atoms. So by stopping the spark and measuring the light straight away after, we can perform TRS with CMOS detectors. So this means that we can eliminate a lot of the background and reach lower detection limits. This also allows single spark evaluation. So single spark evaluation measures single sparks, and that can show you if you have any inclusions, because when you initially spark a sample, if there are any inclusions, you might get a really high peak, which gradually then stabilizes. So if you're measuring the full spark, you get a slightly higher measurement, but it wouldn't be anything alarming. The software can now look for outliers in single peaks, so you can match these up to inclusions that you might be expecting to find. So now, with CMOS detectors, spectrometers can match or exceed the performance of PMTs, and you still have the maximum flexibility and the ability to add new bases and new elements on site. So what do we have today? So for modern instruments in the high-end range, we have the Spectro Lab S that I just mentioned. So this instrument has TRS and single spark evaluation capability. It has low detection limits. It's quite fast, so if you have a high throughput place, so it's advantageous there. And they all have iCal. So this has iCal 2.0. In the mid-range, we have the Spectro Max. So you can't do SSE or TRS on this, but in a lot of cases, you don't need that. It still has good detection limits, and it can be a benchtop or a floor standing instrument. Again, you can use iCal, and again, it's really flexible, and you can add different matrices and elements on as and when you need them. We have the Spectrotech as well, which is a little bit smaller. This one only has iCal 1.0. And with each new instrument, argon reduction is being reduced. For mobile instruments, so these are much smaller than the one before. But we still have the Spectro test. This version is shown there in the picture. Again, it uses iCal 2.0 and CMOS sensors. It's flexible, so you can point and choose at larger samples if you take it out onto site. You can use arc or spark with this. So if you just want to sort through a load of metal, you can use arc excitation, or you can use spark, and you get a few more elements there. So you can do carbon, phosphor, sulfur, and have a UV optic as well in the probe if you're using argon. There's also the Spectro port, which is very similar, just a little bit smaller. Still uses iCal 2.0, and you can still take it out on site. It has a touch screen and more basic software, so it uses plugins instead compared to the Spectro test. And that's it. Any questions? That's gone really fast. Yeah. Yeah. Yeah, if it's grey iron. But if you can cool the sample really quick and produce a white iron for sampling, then you can get a better carbon reading. Yeah. Yeah, exactly.
I'll take that. Just it won't be. Hold on, 1 minute.
No, I don't know exactly which one we would do.
Oh, hold on a minute. It's going a bit quick. They won't hear on the video link.
The question was, are the CMOS sensors unique to Spectro, or are they available on other manufacturers as well?
It's all right.
No, they're available with other manufacturers as well. Anything else?
So I'd invite Martin to give a vote to that.
Thank you very much, Danielle, for coming down from Manchester to give us this very informative talk. Sorry, there's only a few people here to hear the evening. Everybody, thank you very much.
Thanks, Martin. Right, before we finish, I just